Hi there, we're talking about topic 5, which is operations with probability. The last video we talked about the introduction to probability and just some vocabulary related to that topic. Today we're going to talk about some vocabulary related to different types of events and the different formulas related to each of their probabilities. First, let's talk about some vocabulary. So we have disjoint or mutually exclusive events. There's two different names for it. These are events where if one thing happens, it determines that the other thing can't possibly happen. Something like flipping a coin. If I flip a coin and the event that we got a head up happens, then I know for a fact that tails up couldn't have happened. So they're disjoint, they can't happen at the same time. Independent events are when one event happens and it doesn't influence a second event at all. So this is the opposite of disjoint. In disjoint, I know for a fact what's going to happen with event B because of event A, but in an independent event, I can't tell you what's going to happen with B because it's completely independent of what happened with A. So a good example of this is like if we threw a die and also drew a card from a deck. They have no influence on each other. If I roll a 1, it doesn't mean anything in particular is going to happen with the deck of cards. Completely separate. Dependent events are when one event happens and it influences the second event happening, whether that's good or bad, whether it's that B can't happen at all, or if it just changes the probability of B happening. Dependent is pretty broad. Disjoint is a type of dependent event because the event A influences directly what happens with event B. An example of this would be if you drew 2 cards from a deck, one after another. The fact that you drew a certain card in the first draw influences the chances of you having a certain card in the second draw. So for example, if I pulled a card and the first one I got was a king, the kings have a smaller probability of being drawn in the next draw. So it affects the other. The last vocabulary word is conditional events. This is usually used for conditional probability. It's looking for the probability of something happening given that you assume a certain result in the first event. So this is a completely different example, but let's say I wanted to know the probability that a student plays sports. That's one type of probability. But if I say I want to know the probability that a student plays sports given that they are a male, that means first I would have to limit my event to just males and then check for the probability within that subgroup. So the fact that I have this condition can change the probability of the event happening. Beneath this, I have quite a few equations. All of these are on the formula chart somewhere. The big deal is to know whether an event is mutually exclusive or not. If it's mutually exclusive, it has specific conditions that are only true because A and B cannot happen at the same time. But there are a lot of similarities between the any and the independent rows. For the mutually exclusive, if we think about the conditions in which that would happen, it's when A happens, B can't happen. So the symbols, probability of A or B, you would just add the two probabilities together, and there isn't this overlap that takes place in the other two versions of this equation because A and B can't happen at the same time, so you don't have that overlap. What I like to picture is then that Venn diagram, like what we drew in the last video, that let's say this is probability of A, and this is probability of B. This section right here is that A and B. Well, in a mutually exclusive one, those two circles don't overlap at all, which also helps to explain why the probability of A and B is 0. And then this last column is the conditional probability, saying what's the probability of A happening given that B already happened? Well, if they're mutually exclusive, they can't happen at the same time. So if B already happened, we know that A couldn't have, and that's why that probability is 0. In the independent row and in the any row, we have a lot of similarities. One big difference that I see is this one right here, the probability of B versus the probability of B given A. This is actually how we test for independence, or one of the ways that you can test for independence. If the probability of B given that A has already happened is equal to the probability of B, let me write that down. If the probability of B happening after A already happened is the same as the probability of B happening regardless, then that means A and B are independent. And that is because in that first calculation, A didn't influence B at all, since it turned out to just be probability of B. So that's one way you can test for independence. And then this second, or this last formula here, is one of our formulas for calculating conditional probability. It's the only time that conditional probability counts is when it's not independent, in which case there's no conditions that would affect the next event. And if it's not mutually exclusive, then you can use this formula to find conditional probability. That's the only time it would actually matter. Let's finish up by looking at a few examples just to see how we can decide what type of probability we're looking at and which equation we should use for that example. So here we have a single die being rolled. Find the probability of rolling a 2 or an odd number. So I first focus on that word or. That means we're going to be using the second column from our chart. And we have to decide, does the first event influence the second event? In this case, rolling a 2 doesn't have anything to do with rolling an odd number because 2s are not odd numbers, and odd numbers don't include 2. So these are going to be mutually exclusive because if I roll a 2, then I couldn't have rolled an odd, and if I rolled an odd, it couldn't have been 2. They are exclusive. And so we're going to use the formula from the mutually exclusive table with the or, which is just probability of A or B is just the probability of A plus the probability of B. So we have the probability of event A, which is rolling a 2. That's one number on a 6-sided die, so that is 1/6, plus the probability of the second event, which is odd number. Well, that's half of the numbers on the die, or 3 out of 6. And so we would just add those together, and we get that you have a 2/3 probability, or 66.7%-ish chance of rolling a 2 or an odd. Here's our second example. Suppose that we have a town and 54% of the population has brown eyes, 51% of the population has black hair. Those are separate characteristics that may overlap. And 37% have both brown eyes and black hair. What is the probability that a randomly selected individual will have brown eyes or black hair? So in this case, because we could have both events at the same time, you can have both. In fact, we have some group that has both. This is not mutually exclusive, but, and it's not independent because having brown hair could change the chance that you have brown eyes or vice versa. So they are not completely separate either. There is a chance that having one of these features will influence how likely you are to have the other. So we're going to use the any column or the any row, and we're looking for an or relationship. So we're going to use the formula for probability of A or B, which in this row is the probability of A plus the probability of B minus the overlap. And we talked about that a little bit last video. The overlap has already been accounted for in the A plus B part, so we're just trying to not duplicate that calculation. So the probability of A, let's say that's the brown eyes, and probability of B, let's say that's the black hair. So brown eyes would be 0.54, and black hair would be 0.51, and we're subtracting away from that the chance that you have both so that we're not duplicating that calculation. And just using a calculator real quick, I got 0.68, which means you have a 68% chance of having at least one of these two features, brown or black hair. The follow-up question is, using the same information, what is the probability that a randomly selected individual has brown eyes given that they have black hair? So this is talking about that independence. If these two features were independent, it would not matter that they had black hair. The probability of having brown eyes would be the same regardless of having black hair or a different color hair. But it is possible that it could have an influence. So we're going to use the any formula. And if it just so happens that this probability is exactly the same as the probability of having brown eyes from the given problem, then that means the events were actually independent. And that's a test that we can do to check if two things are independent. So we're going to assume that they're not, just for the beginning. And this is conditional. A given B. So copying down that formula, A given B is the probability of having both features divided by the probability of having the black hair, which is the feature we're assuming that this person has. So the probability of having both is 0.37. The probability of just having black hair is 0.51. And dividing those, I get approximately 0.73 or 73% chance. So that's pretty high, and that is not the same as the probability of having brown eyes for the entire population, which means that there is an increased chance of you having brown eyes if you're part of the population that has black hair, and that means that these two features are not independent of each other. All right, hopefully those few examples helped, and the equations are going to be nice and organized for you to find which equation you need to work with at a given time. Here's that list one more time. Thank you guys for watching, and we'll see you in a few more videos.